what is alternating current? That means voltage you have in your house, the 220 volts that powers your lamp, your bulbs, are in alternating current. And direct current are those typical ones you see from your batteries, your phone charger output. They are all direct current. What's the difference between the two? Alternating current means that the current is going between 0 and 220. In fact, from minus 220 to plus 220. It's moving in that form, and it's moving at the rate of 100 times in 1 second, if I'm right. So that's alternating current. But direct current is just a straight line, a straight voltage, no alternation. And the reason for alternating current is simply because of cost of transmission. So transmission line does better when the current is, albeit your gadgets, your televisions, your radios, your phone cannot use alternating current. They use direct current. There ends the need for conversion. So in your typical home gadgets, let's say in the olden days, you will have a transformer in your device. A transformer is that which steps down that 220 volts to the voltage that is required by your device. Some devices 12 volts, some use 5 volts, some use 9 volts. So you have transformers like that that can step down to 20 volts to 12 volts. So let's take 12 volts for example, or let's take 5 volts for example. You have a transformer that can step down to 20 volts to 5 volts. So the 5 volts at the output of that transformer is still alternating current, and you cannot plug that directly into your phone. It will not work. So what you need to do is to add a rectifier circuit that will convert this alternating current to direct current. Do you get? So let's quickly do an experiment to see how that works. So here I have my simulation circuit. I will just go to a pre-drawn circuit. Let's see, full wave rectifier. So I have that here. So this is a circuit of a full wave rectifier. You see it contains 4 diodes. Let me stop this simulation. It contains 4 diodes, 1, 2, 3, 4. And this is your AC signal, and this is your load, maybe your phone charger or something. Or this is or a bulb. This is your load. So it contains 4 diodes in this configuration. Take note of the configuration. So this is how I used to do it before I run the simulation. So current, I told you that alternating current flows in both directions. It can flow up, it can flow down. So when say the direction changes. So when the current flows in this direction, so that means the current will flow like this, in this manner. Then when it gets here, the current will not be able to flow like this because this is a reverse bias diode. It will block the flow of current, but the current will flow in this direction. This is a forward bias diode. Do you get that? So the current will flow like this. When it gets here, it won't flow back here. Do you get? It's a reverse bias diode. So it will flow through this resistor or through this load, then go back like this and gets here. Now, when it gets here, what direction do you think the current will flow through? Is it here or is it here? All right, it's going to flow through here. Why? Now, here, the voltage at the cathode of this diode here is more positive. Remember, the voltage came through here. So let's say this is like 7 volts that was coming like this. When it got here, this is 7 volts here. When it got here, it's still 7 volts, but this diode will drop 0.7 volts. So diodes drop voltage. It drops 0.7 volts from your voltage. So this one will drop 0.7 volts. So that means by the time it's getting here, it has become 6.3 volts. By the time it passes through the load, and or maybe it has become 6 volts. So when it gets here, this place will be at 6 volts, this place will be at 7 volts, thereby making this diode reverse. So the voltage here is greater than the voltage here. So it won't flow. No, the voltage here at the cathode is greater than the voltage here at the anode. So the current will not flow in this direction. It will rather flow in this direction and then flow back through this to complete a full circuit. So let's twist again like this, 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 in this way, then back to. So when the direction of the current reverses so that it flows in this manner, so you're going to have it like this. When it gets here, the current flows through here, then goes like this, then goes like this, goes this way, goes this way, goes this way, and return through here. So that's a short demonstration of how alternating currents and rectifiers behave. So let's do this in real life scenario. I will move this away a little. Let's move this also a little. I want to add a transformer. Let's add a transformer. So I told you earlier, oh, sorry about that. I told you earlier that you need a transformer to step down the voltage. So we want to bring in that transformer. So we have this transformer connected. Let's change this to 220 volts. I'll do that by double clicking here, and I will change it to 220 volts and set the frequency to 50 hertz and apply. Click OK. I'm going to connect here, draw wire. Then I'm going to connect. Okay, that's good. So let's see. So this transformer is acting like a 220 volts to a step down voltage. How did I know? So this is the input side. This is the waveform at the input side, 220, and this is the output side, 6.52 volts at 100 ohms load. So you can see this is the waveform of the alternating current. You can see how it goes up and down. This is a positive, up here is a positive region, and down here is a negative region. This other waveform is the current flow through the transformer. Well, let's ignore that for now. So this is negative region. It goes into negative to positive to negative like that. But on the other hand, at the output here, you can see is only positive, but it is pulsating between 6 volts and 0 volts. 6 volts and 0 is moving between 6 and 0. So this is a pulsating DC, right? So that means it's not a perfect DC, it's a pulsating DC. So for this circuit, this will be your positive side and this will be your negative side or your ground. So this is what the input looks like. You see that alternating. You can see the voltage also moving between minus 220 to plus 220. Albeit on the output side, the voltage is direct current but pulsating direct current and is moving between 6 and 0. So now that takes us to the next part in this power supply circuit. So if you also, before we move on, look at the flow of current. Do you see that? Then reverses. So look at the flow of current around this diode. I'll let that run for some time so that you can see it clearly. From here, then reverses. So at a point, only two diodes are conducting points like that. Let's move to this part, which is one of the uses of a capacitor. So in our course about capacitor, when we are studying about capacitor, I mentioned that capacitors are used for filtering in power supply circuits. Capacitors are used for filtering. Now that we're in power supply circuits, let's talk about what does filtering means. So let's go back to our waveform, and we're going to add the capacitor here. So let's move this forward, let's move this away a little, and let's bring in a capacitor. Let's add a polarized capacitor. Good. So we're going to move this load away for now. Let's add a polarized capacitor here and the load here. And we're going to connect. Good. Now let's start this simulation. Let's bring this one closer again. Let's start the simulation. Okay, the changes is not that much. Let's increase the value of this capacitance. Let's say 1000 microfarad. You see now that the waveform has smoothing out. It has smoothing out entirely, but you see a little pause there. I wish I can zoom in. Oh, good. You see a little pause there. You see a little pause on the waveform, right? So that's filtering. You have filtered out the pulse in that direct current. Now, the larger the capacitance, the more filtering or smooth your power supply will be. The smoother it will be. Albeit, there is also an economic reasoning to these things. So I want to advise, if you are doing 5 volts power supply, 12 volts, 1000 microfarad is enough. All right. So, but there's something I can do. You know, this 100 ohms load is, let's change it to 1000 ohms and see the difference. Now, at 1000 ohms, it's almost as though everything is now totally smoothened out. Everything is smoothing out. The amount of the load will determine how clean your direct current will be. Okay, finally, let's add one more, since we are already talking about power circuit. Let's add regulation. So I mentioned Zener diode the other time, right? So let's bring in Zener diode into this circuit. So this is a Zener diode. It has to be in the reverse direction. I will move this away. I'll move this away, bring the Zener diode in. Now, one rule when you are adding a Zener diode to your circuit, you must place a resistor between the power line, within that power source, and the diode in this manner. So the value of this resistor is determined by how much current that your Zener diode is meant to handle, right? So using the same principle of how to get the resistance of a light emitting diode that you connect in series with a light emitting diode, you can use the same formula here as well. So for example, if this Zener diode is rated at 1 watt, a 1 watt Zener diode, 1 watt at 5 volts means that the amount of current that it can allow maximally is 1 over 5. That's around 0.25 or 0.2 amperes. So you must condition the value of this resistor to be able to do that and not pass the amount of current it can supply. So let's just assume 100 ohms is enough. Let's see if we can change the value of this, the voltage level. Okay, good. 4 voltage saturator, breakdown voltage. Let's change it to, we need it to be maybe 5 volts, 5.1 volts. And click OK. And click OK. Now, let's start this simulation. Let's see if we can add a meter or something. If there's a meter there. Show voltage, show power. Okay, I have it already. Let's start. Let's run the simulation. Now, when I click, sorry about that. Now, look at the voltage here now. Number one, the line is perfectly smooth and the voltage is steadily at 5.111 volts. 5. Let's zoom in. The line is smooth. The voltage here is at 1.111 volts.